Okay, in the previous class, we discussed, I told you the fascinating story about how statisticians in the second half of the 20th century believed that if you characterize your linear regression model with even one number, r squared, that will tell you the whole story, right? Because, as we discussed, r squared is the measure of the model accuracy, in a way. Okay? It tells you, again, generic interpretation of r squared is it tells you the percentage of variability in target variable y, which is explained by variability in predictor variables x axis. Okay? That's generic interpretation. So the higher r squared means more accurate model, right? Your predictors explain more variability in your target, therefore it's a better model. Well, and I told you that there was a statistician by the last name Anscombe who published a paper, I can't remember when exactly, 1970s or 80s, and in this paper he was trying basically to tell the following story. R squared is not everything, okay? You can't just give me a handful of numbers and tell me, hey, look, this number is looking good, so therefore it's a good model, okay? It makes sense, oftentimes, to look at the picture. So, and I believe that his data set, he published actually 4 data sets, I told you, right? And that's why it's called Anscombe Quartet, as in 4, okay? And it's so popular that it's built in RStudio. So, go ahead and create a new script, clean script, just like what we did last time, right? And if you start typing Anscombe, you will see that it's already there, okay? So, just go ahead and, so it's loaded in the memory already, okay? We don't even need to read the file, it's already there. So, go ahead and hit run, and it will show you the Anscombe Quartet. So, there are 4 pairs of variables, x1, y1, x2, y2, etc., okay? And you can see that each set contains only how many observations? 11, right? Not a huge data set by any stretch. So let's do this. Let's go through them one by one and see what kind of model are we getting, okay? So let me go ahead and run the first model, okay? So I'm going to call it model 1. Model 1, okay? And remind me again, which function do we use to create linear model? LM. L, linear, M model, LM. And in the LM, all I have to do really is to tell what's my target and what is my predictor, right? So my target is Y1, all lowercase by the way, okay? Tilde, predictor is X1, and the data to use is Anscombe. Let's show, okay? So go ahead and run this line, and it should give you no problems. Should show you no green color, just the blue, right? And now let me look at the summary, okay? So I have variable x1, whatever it is, and variable y1. x1 is predictor, y1 is the target. So let me take a look at the summary. Okay? Summary of my model 1. Bam. Here is my summary. Okay, now ladies and gentlemen, by looking at the summary, can you tell me the equation of my model 1? Okay, I'm here typing it, okay? Pound sign, tell me, what's the equation for the model 1? Y1 equals what? Here's the output. 3. What's the next one? 3 is my intercept, right? What's my slope? 0.5, plus or minus? Plus, right? Plus 0.5 times what? Times my predictor, which is x1, right? This is my model, right? Y1 equals 3 plus, okay, 3 plus 0.5 times x1, right? Do you agree? Based on this output, this is my intercept, here's my slope. Slope multiplied by x1, that's it, okay? Where's my r squared? Well, r squared is right here, okay? 0.665. Is that a good r squared or not so good r squared? It's an okay r squared, right? It's not great. All right. Let me go ahead and get a picture of my model 1. I need to do the scatter plot, right? Okay, so how do we do scatter plot in R? We just say plot, right? If you want to use built-in function, I have to tell what my x is, and that would be anscombe $x1, that's what I use, right? And what's my y? It's going to be anscombe $y1, right? And that is my picture right here, okay? X horizontally, y vertically, and you know what? I'm going to plot also the linear regression, which I obtained in my model. Remember how to put the line for your model on the plot? AB line, right? I'm going to say AB line, plot me model number 1. And if I run this command, then there it is, okay? So, does it look like a decent plot, decent model? What I'm looking for really is this, okay? My points will not align perfectly on the straight line, right? Almost never. So therefore, what I'm looking for really is this. The line cuts through the center of my point cloud, right? And roughly speaking, I have same number of points above the line as I have below the line, right? So I represent kind of the middle of my data set, okay? So does it look okay, the plot? Scatter plot? Yeah, looks fine, right? Because I have several points above, several points below, seems evenly distributed, so looks fine to me. Okay, but this is a good model. All right, I believe I told you that good programmer should be what? Lazy, right? That means that I don't want to type this thing ever again. I'm going to copy paste. So model and everything else, I'm going to say copy and paste it right here. I'm going to call it model 2. Okay, and this time around, I'm going to use my y2 and x2 to other columns from anscombe dataset as my dependent variable, target, and predictor, okay? And I want summary of my model 2. And let's see what I get, okay? So I'm going to run model 2 right now. So the only difference, again, I'm using x2 as a predictor and y2 as a target. And I'm going to call it model 2, right? So I'm going to get summary. And here is my summary. Well, did you get model 2 on your computers?
Not yet.
Not yet? Okay. Get model 2. Get. Who got model 2? All right. Tell me what's the equation for model 2? y2 equals what? What's the intercept for model 2? 3. What's the slope? 0.5. It's the same model. Oh my god. And what's the r squared? 0.66. So judging by the r squared, model 2 is just as good as model 1, right? If I don't see anything else, just use r squared. Model 2 is just as wonderful as model 1. But let's do the plot, okay? So I'm going to plot x2 horizontally, y2 vertically, and I'm going to fit also the model 2 line, okay? So run these two lines. Scatter plot for x2 versus y2, and then fit the line. Oh, Jesus. Do you see that? Do you see what I see? These points, are they on the straight line? What does it look like? It looks like parabola, right? But we still have the straight line, which apparently is the best fit into our data, right? But true or false, this straight line does not really represent the points nicely in any way, sort, or shape. True, right? But if I didn't see this picture, I wouldn't know it, right? My R squared is the same, my model is the same, everything is the same, but you look at the picture and it's like, oh my god, linear model is not a good thing here, right? All right, let's do the third one, okay? So you get into the spirit of Christmas, right? So again, good programmer should be lazy, so I'm going to get copy-paste. All right, and I'm going to call it model 3. And my target is going to be Y3 versus X3. Same data, I'm going to run it. And I'm going to get summary of model 3. Okay, you guys, did you get the summary? You tell me what's the equation. Three plus 0.4997, which is what? 0.5, right? Okay, so it's the same equation, really, right? And what's the R squared? 0.666, same exact thing as in my model 1 and model 2. Well, let's do the scatter plot, okay? Let's do the scatter plot and AB line. All right. Oh my God. What do you think is going on here? Any ideas? The what? Exactly. Don, do you remember you're asking what outliers will do? That's exactly the answer, okay? If you remove that lonely point up there, then I'm guessing this point align perfectly. Your coefficient of correlation will be almost perfect 1. Your R squared will be really close to 1.0. But because you have this one point out there that tilts the whole line, right? This point basically says, I'm a sort of a source of gravity. Okay, I'm going to tilt the line towards me, and therefore you have no good fit anymore. That's what outliers will do to you. Okay, that's why every time when data scientists, people who do the data analytics, they do linear regression, you have to be looking out for outliers, because that can happen. Okay, it will distort your picture and it will make your model worse and maybe not usable at all. Okay. So outlier basically screws things up for us right here, right? But if I didn't see the picture and used R squared, would I know this? No, right? This would be completely mystery to me, okay? I would say 0.66, not bad actually. All right, and let's do the last one, number 4, model 4. Last pair of points, that would be Y4 versus X4. And plot the model 4. So, okay, so tell me what's the equation from the summary. Y4 equals what? 3 plus 0.5 times X4, agree? That's my model 4. Slope is 0.5, intercept is 3. Same equation. What about R squared? 0.666, same exact R squared, right? This model just as good as 3 that I had before. All right, let me do the scatter plot of my last X4 versus Y4 and model 4. So I'm going to run both of them. What do you think is going on here? Yeah, outlier, but that's a little bit actually more complicated. True or false? If I remove this lonely point in the upper right corner, then the model becomes truly weird. It's like all the points are right here, x equals 8 and y equals 2 all over the place, right? So what model is that? That model basically tells me that x is always 8, but y can be anything really, right? It's not even a model, strictly speaking, right? I can predict y if I know x, so there is no model. But this point, as an outlier, says, no, now I give you the sense of direction, okay? You have to go through me now, okay? So before that, we didn't have a model, and this point says, yep, now I will define the model. You will go through me, and then center of the rest of the points, okay? This is something that's called influential observation, okay? Here is another example, right? Let me give you an example of influential observation. Suppose, for example, I have x versus y that looks like this. I have truly random cloud of points, okay, like this. Okay? There is no straight line, agree? If I have picture like that, scatter plot like that, there is no model, right? What is it? Is it like this? Is it like that? Is it more horizontal? Which one is it? Can be anything really, right? So I look at this point and I have to say I don't have anything really going on, right? But if I have a point somewhere on the outskirts of civilization, then immediately my line will go through that. And that's going to be the only possible, the best fit, okay? So therefore, this point is called influential observation. Influential observation. You understand why, right? Because without this point, there would be no model. But once this point is there in place, immediately it tells you, yep, now I have the model. Okay? And this is also a bad case, right? Because strictly speaking, this is, you can treat it as an outlier, right? Which by itself, single-handedly defines the whole model for you, okay? Not a good thing, really. You want the majority of your points define the model, not just one of them, right? So, that was the idea behind Anscombe's publication, okay? He wanted to show people that, hey, you know, numbers do not tell you the whole story, okay? So you can get great R squared, but that doesn't mean that your model is good or bad. You need to take a look at the picture, right? One picture is worth thousands of words. You can tell a whole lot by just looking, okay? So, plotting the scatter plots, fitting straight lines and seeing how points are distributed according to your, relative to your model, that actually will tell you a lot, okay? Speaking of which, by the way, let's discuss residuals. How many of you remember the word residuals from statistics interclass? So? Alright, let's discuss residuals. I'm going to switch back to the Corolla simple regression, the model that we had before, right? You still have script, right? Yeah, you should have script. So, let's go ahead and run the entire script so that everything is in our memory. Okay, hold on. Run. Come on. Here is the plot. My plot doesn't want to refresh. Did you get the plot? You did? Okay. My plot doesn't want to refresh, so how about I'm going to clean my memory and do it line by line. Oh, come on. Reload. Okay. Amazing case of software resistance, right? Alright, my plot doesn't want to reload. Hold on, give me a second. Did you get the plot? Mileage versus price versus mileage? You didn't? Alright, hold on. I'm going to close that. Don't save. And reopen that. Corolla. Uh-huh. Error plot.new has not been called yet. Well, that's amazing. Huh, that never happened before. Typically it does not resist. Ah, okay, here. Error, object, Corolla not found. Oh, it says Corolla not found. Corolla data. Oh, I see. Okay. So I call it Corolla data. Corolla price, what? In plot, Corolla data, oh, Corolla price, yeah, you're right. There it is, Corolla data, right? That's why it says, what's Corolla, right? There is no such thing. Okay, thank you. Corolla price, yeah. And there it is, thank God. Alright. And then coefficient of correlation I'm going to skip. So I'm going to run the same line right there. Linear regression model, summary, AB line. Okay, so here's my plot, right? One way how we can judge if your model predicts things more or less acceptable, nicely or not so nice, is calculate something that's called residuals. So let's discuss residuals. Okay, so what are the residuals? Here's what typically happens. Okay, so suppose I have, let me just say that I have 6 data points that look like this. Okay, so this is my mileage, this is my price right here. Okay, and you can clearly see that there is a trend, right, that goes on in this picture, and the trend looks like this. Right? Okay. Cool. So ideally, here's what I want. My model, and we discussed that earlier today, my model should have, roughly speaking, same number of points below the line, below the equation line, as the number of points above the equation line. That's one thing. Another thing is this. The points should be, roughly speaking, have the same distribution above. The residuals, positive residuals, should have the same distribution as negative residuals. Okay. So what do we mean by residuals? Again, the word from your BU Center 31, right? Residual is an error. That's a scientific way. Residual is an error, scientific way, kind of, to say what are my errors, and that is actual minus predicted. Okay, predicted. So here's where the residual comes from. Okay. Let's take a look at this car right here. Okay, it has X1 mile on it. All right. What is my prediction for this price, for this car? Prediction is right here. This is my Y. This is actual. It's not predicted, but actual. No, sorry. This is predicted. Yeah. Can get my stuff together, right? This is predicted. What's on my straight line? Right. That's prediction. But this is actual right here. So this is Y actual. Okay. So if I subtract Y actual minus Y predicted, in a sense it will tell me how far off I was in my forecast for this car, right? My prediction here was higher, you can see, right? But the actual price was lower. So the residual in this case, let me call it error number 1, is positive. Agree? My no, negative. Man, what do I do? E1 is negative because actual is lower than predicted, right? See, the price actually was lower, but I predicted to be high, okay? So this is my second car right here, okay? Let me erase this point. Let me put it right here. This is my second car. This is the actual, right? And this point on the line is predicted, okay? Again, I didn't guess correctly, right? There was an error between what really happened and what my model said would happen. Okay, so in this case, actual minus predicted, actual is higher, and the error number 2 is what? Positive, right? Here is another one, right? This is car X 3 mile on it, okay? This is the actual, which is lower than what's on my line, and that is predicted again, right? Predicted. So if I take lower actual minus higher predicted, the error is going to be negative again, right? Less than 0. Some errors are positive, some errors are negative, okay? And that's what good model will do. It will cut through the center of cloud, which means some points will be above the line, the model, some points below, okay? Therefore, your errors will be sometimes positive and sometimes negative. So roughly speaking, and errors are called residuals, right? We just discussed that. So roughly speaking, same number of positive residuals as the negative residuals my model should have, right? Half and half. Half residuals are positive, half residuals are negative, okay? That's one thing. So ideal residual plot, ladies and gentlemen, let me show you the ideal residual plot, okay? So this is residual error, okay? Error. Some errors must be positive, some errors must be negative, right? So this should be the ideal residual plot, okay? And moreover, your individual errors, these are dots on my scatter plot, right? Individual errors must be distributed evenly in the positive area and in the negative area. So if you imagine that as a cloud of points, right? This is imaginary boundary of clouds, okay? The thickness of the cloud of points should be the same everywhere, okay? So it should not get more narrow or more broad, the residual distribution. It should be uniform thickness, okay? That's number one. Number two, you should see no patterns in the residuals. What do I mean by that? Remember when we just looked at Anscombe data set, remember the data set that looked like this? And Cooper told me this is called what? Parabola, right? So remember that? It was data set number 2, I believe, right? And we feed the line that looked like that. Do you remember? Yeah. So this residual is positive or negative? This error, first error. The actual is lower than the line, than the predicted, right? So this is negative, right? And if we have another point here, this is also negative. What happens to this point? They're all positive, right? So these are all positive. And then again, let's say we have another point right here. These are again all negatives, right? So if I plot the residual plot, it will look like that. First they were negatives, right? Negative, 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 then they became positive, 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 and then became negative again, right? I could see the same pattern in my residual plot, okay? That's a big no-no. Your ideal residual plot should look like this, okay? It should be cloud of points, random, with no pattern. Any type of pattern that you can see. It can be a sine wave, it can be a curvature, it can be trend. Residuals were positive, and then they became all negative, and they remain negative, okay? Any type of pattern is a bad indication. That means that your model is not exactly linear, or you have an outliers that influence your line, or you have influential observation. Anything, something is going on, okay? Your model is not ideal. Its usability is very limited, okay? Does it make sense? So, residuals analysis, okay? Well, alright, with all this hoopla, let's go ahead and do it, right? After all, this is a lot of theory, but let's actually go ahead and do it. Alright, so how do I calculate residuals? I have a model, right? Let me go ahead and calculate the residual. Well, there are a couple of ways to do it. There is an easy way and a hard way. Do you want to see both of them? Easy one. Okay, well, let me show you the hard way first and then the easy one, okay? Easy. First of all, I need to predict my prices, right? Then I have the real prices, I have to subtract the actual minus the predicted, and that's my residuals, right? So, prediction. Predicted prices. Okay? From your distant memories of about several weeks ago when we discussed classification trees, how do I use my model to predict? Which function do I use? Predict. Right? I'm going to say predict. And I have to say the model, right? What's my model name? My model is called, hold on, where is my model? Here. My model is called, really long name, Corolla Simple Linear Regression Model, okay? And the new data to use is the same as the old data, and that would be the Corolla data, right? Corolla data. Then. Okay, so I run this line. It should create no animosity from our studio. Okay, so essentially what I did is I took my model, which looks like this right here, right? And for each data point, how many data points do I have in this data set? I believe it's 1,000, if I remember correctly. Each one of these 1,000 cars, right? The R took the mileage for each of the cars, plugged that mileage into the equation, and calculated the predicted price. That's literally what happened, okay? I can see the prices that I predicted if I just type predicted prices, hit enter, and there it is, okay? 1,000 predicted prices for 1,000 different cars, okay? Based on their mileages, right? This is simple regression. We use only mileages and nothing else, remember? Okay, so after that I can say, okay, let's calculate residuals. Residuals is, how do I calculate residuals? Actual minus predicted, right? We just discussed that. How do I find the actual prices? Any ideas? Corolla data $ prices. That's where I keep them, right? Corolla data $ prices. That's the real price, right? Minus predicted prices, right? That should basically do it. Okay? So let's go ahead and run it. Run this command. So it takes 1,000 real prices, subtracts 1,000 predicted prices, gets 1,000 residual differences, and now let me go ahead and plot that, okay? So, well, how about I'm going to plot, just say scatter plot, plot, right? And that would be my y, agree? My residual should be vertical, right? So what should be my x? Well, how about I plot it versus mileage, okay? Depending on the mileage, how much error am I making in predicting the price? So therefore, I'm going to say Corolla data mileage, that's x horizontally, and the y is going to be the residuals themselves. Residuals. There. Okay. So this is what I'm plotting, right? X horizontally is the mileage, y vertically are the residuals themselves, okay? Alright. Well, by the way, ladies and gents, what should be my average residual, ideally? Average error, if you would have to guess. Remember we discussed that half of them are negative, half are positive, right? That's ideal. Average should be 0, right? Does it look like I have average 0? Kind of hard to say. 0 is right here, right, in the middle. Yeah, but does it look like a uniform cloud of points to you? With the same thickness everywhere? No, not really, right? Because for low mileage you can see that the residuals are all over the place, right? They range from minus 5,000, roughly speaking, to plus 10,000, right? And as I get to higher and higher mileages, the residuals are becoming less variable, right? So in other words, I have pattern not like this, right? But more like, let me scroll it down a little bit, erase all that stuff, okay? I have a pattern that looks more like this. This is 0, right? The residuals were pretty high, and then they slowly became smaller and smaller and smaller. I see a pattern like this, agree? In my residuals plot, right? Here's my residual plot, so you can imagine kind of a conical shape going on, right? Would you agree? Say meow. There you go. Alright, so this is not a good sign, really, right? And this, in statistics, is called heteroskedasticity. Skedasticity, okay? Heteroskedasticity is not a good thing. Means that your residuals are changing depending on where you look, like in this case mileages, right? As the car becomes newer and newer, less and less mileage, the residuals are getting bigger swings, right? The variability increases. That's heteroskedasticity. This pattern, by the way, that doesn't have, this is ideal pattern, right? This is called homoskedasticity. Homoskedasticity. So ideally your residuals must be homoskedastic, okay? That means that variability of residuals does not change. It looks like a uniform cloud of points with uniform thickness everywhere, okay? Any questions? Make sense? So if you, yeah, this one is called heteroskedasticity. By the way, there is another pattern possible, also called heteroskedasticity. It's when your residuals look like, let me get rid of this stuff, when your residuals look like this, okay? For, let's say, in this example, right, for low mileages, it's small variability, but as you're getting higher and higher mileages, the swings are going to be higher and higher. So in other words, it's also non-uniform, but in an opposite direction in a sense, right? So, either way, your residuals have a pattern like this, conical shape, right? It's called heteroskedasticity. Not a good sign, not a good indication. Okay. Yeah, both of these patterns are called heteroskedasticity. Okay. Yeah, that's basically a warning sign. Okay. That means that really what that means is hold on. Our model can better predict, more consistently predict prices at high mileages, right, as opposed to low mileages. For low mileages, your variability will be all over the place, okay? But as the car is getting older, then your prediction is getting more accurate. So you're getting less errors, and they're more consistent, right? They're more concentrated around zero, okay? Which probably makes sense, right? Because as the car is getting older, their prices don't fluctuate all that much, right? It's the brand new cars or barely used, that's when you have big differences, right? So it probably makes sense from that standpoint, okay? All right, let's do another one, okay? Another condition that we have to make sure happens is all of these models, they're good and usable if the residuals are normally distributed with the average of what? What should be the average residual value? 0, right? I want to have average error. Some are positive, some are negative, but on average it should be 0. So if I do this, the histogram, not the scatter plot, but the histogram of my residuals, they should look like normal distribution with the center of 0, right? To the middle of 0. How do we do histogram? Do you remember? We did that at the beginning of the semester. Anybody remembers? Really simple. H-I-S-T, hist function. We did that at the beginning, right? Or did we? We didn't? Probably not. Okay. All right. New function today, HIST, histogram. Okay. So let me go ahead and plot distribution of my residuals. Okay. So I'm going to plot residuals. Ideally, they should be nice bell shape with the center of 0, right? The midpoint of 0. Okay. So here's the histogram of my residuals. Okay. What do you think? Does it look like the average residual is 0 for me? Yeah, probably, right? It's right here. Some residuals are positive, some are negative, so that's okay. Does it look like it's more or less bell-shaped? Yeah. There is some skewness. If I would have to ask you, is it right skewed or left skewed distribution? How do we say if it's right skewed? If it has the tail going to the right, yeah, positively or right skewed, that means the tail to the right side is longer, and left skewed the other way around. So this one is what? Probably slightly right skewed, not horribly, right? So is that terribly non-normal distribution? No, not really, right? So residuals are well behaved as far as the distribution is concerned, but we still have the heteroskedasticity problem, right? So that is an issue, okay? That means that our model really performs better for high mileages as compared to the low mileages, right? So therefore, each time when you use it, you have to be really careful, okay? Because the prediction you're going to get, you will be off, no question about that, but by how much, right? For higher mileages, your error will be smaller than compared to for low mileages, okay? Make sense? Okay. I have one more topic actually to discuss, but it will require more than 4 minutes. So should we postpone that until Friday? Okay. So I'm going to stop the recording right here, and we'll finish off simple regression on Friday, and we're going to start, guess what? Not so simple, right? It's called multiple regression, when we're going to start throwing in more variables, okay?